All right, so even before I start, I want to have only 2 more quizzes, right? That will bring the number to 10. That's, I think, what I promised in the syllabus. The moment I'm done with cryptography, which probably will happen only after Tuesday, which is still school day, right, next week, I'm going to have a quiz. I'll give you literally a week. So if you have plans for Thanksgiving, you can do whatever and still find time to take the quiz. And then whatever I'm going to teach afterwards, which is probably be something like MapReduce or things of the sort, or mixed up with a little bit of distributed systems, we're going to have another quiz. Okay. Your main concern for now should be the project. So there's going to be no quiz this weekend because I'm not going to be done with the cryptography security. Okay? All right. So let's now start talking more in terms of nuts and bolts of how the security works, especially things related to cryptography. So usually what happens is the discussion about security in general is reasonably loose. The discussion about cryptography, it's extremely precise. And it gets down to actual mathematical notation and actual protocols and proofs that certain things have or don't have certain properties. Of course, I don't expect you to prove anything, right? But it's still important to get some idea of what the notation is and to understand what it means to have a good security protocol. To some extent, what makes a security protocol good is going to be about not leaving any backdoors that can be exploited in any way, shape, or form. So traditionally what happened is certain protocols were proposed. Researchers tried to find a way to break it, to find some scenario under which you could hijack something, and then propose corrections to it to fix it. Okay? Now, obviously, finding the secret keys directly, that's always the best method, right? And we are going to assume that you cannot squeeze the keys out of the person you're trying to attack directly, the keys. You need to work for it somehow, right? So we are mostly concerned about vulnerabilities that make the life easy for the attacker, not, kind of the ultimate one in which you just, if you trick people into them telling you the password, then so be it. But there are some ways you can actually protect against that also. For example, if you use some kind of fingerprints or things like that. But we are not going to touch upon that. OK. So here's some of the notation we are going to have. By KAB, K is going to be keys. Anything with Ks in the slides is going to be about keys. KAB, it's a secret key shared by A and B. Right? Now, this is what basic symmetric encryption is all about. We agree on a key. We both know the key. I encrypt the message with the key, and you decrypt it with the key. Well, technically, you decrypt with basically the XOR of the key to reverse the process. So symmetric cryptography, it's all about reversible garbling algorithms, right? So I'm going to mix the key in a sophisticated way, and we are going to see some examples. I'm going to mix the key with the message. That produces a garbled message that cannot be ungarbled unless you know exactly the same key. Okay? That's symmetric cryptography, right? So a lot of the protocols will require us to somehow establish a common key between A and B. Ka plus is going to be the public key of A, Ka minus the private key of A if we are using the asymmetric encryption. Now, something which is extremely important to get out of these lectures is public key cryptography provides really neat features, but it's expensive computationally. Okay? So the way to deploy it is the following. If I want to talk to you, I'm going to cook up a random key. And that's going to be essentially the KAB, the shared key between us. But in order to tell you what the key is, I'm going to use public key cryptography. And then we can use the symmetric encryption. So symmetric encryption is orders of magnitude faster than asymmetric encryption. So I'm going to use the asymmetric, the public-private key encryption, just to exchange securely a private key with you. And then we are going to use AES-256, which is implemented in hardware or things of this sort, to have very fast communication. Okay? In this way, we have both performance and safety. Right? But what you never do is do all your communication based on this public-private key exchange. Okay? Because it really is slower by at least 2-3 orders of magnitude. There is no interest in making it faster because AES-256 is very secure as long as you don't reuse the passwords too much. If you pick a password and use it for 10 years, then you're exposed because somebody in the meantime has time to break it. But for example, if you exchange a key every 10 minutes, right, that's going to be perfectly acceptable. Right? All right, so that's the notation. Let's move on. OK. Now, the way I don't want to go into all the details. I would strongly recommend you read some book about cryptography. They tend to be fascinating. Okay, it's how people started with very simple cryptographic systems, and then they got them better and better and better, and how at every point in time they believe they have the ultimate method that cannot be broken, and then somebody broke it, and right, things like that. So all of these symmetric cryptographic systems have the same kind of principles, right? And by the way, the principles are very simple. How many of you heard about Enigma, the encryption machine used by the Germans during the Second World War? Well, in fact, there are many similarities between the way Enigma was encoding and all the modern cryptographic systems. The only difference is instead of using only 3 wheels or 5, by the end of the war they switched to a 5-wheel Enigma, you really use something like 16 or 32. Okay, AES-256, I think, has 32 such rounds. But the idea is you are going to interleave one of, but how you interleave them, it's what makes the encryption system strong or not. You're going to interleave operations that somehow garble the data, but you have to garble the data in a reversible way, and the garbling is controlled by the key. So you do certain steps always that do some garbling, and certain steps depending on what the value of the key is, right? So simple cryptographic systems might basically do a garbling if the key is 1 and not do it at a particular stage, but there is other kind of garbling that needs to go on in between to make the system strong. People have tried all kinds of garbling mechanisms, for example, some sort of rotations or some sort of shifts, right? I don't want to go into all the theory, but some of the basic ingredients can be permutation between letters, and then taking the message, maybe create a block out of it, and rotating the letters among them, right? So you have transpositions and permutations, and possibly some other ingredients thrown in there for good measure. The key is going to control some of these things, okay? All of them reversible, right? So simple, for example, simple transposition is to come up, and this is what Enigma was doing with some of the wheels, right? To come with one-to-one correspondence between letters, to say A and T exchange each other, right? B and Z, so on and so forth. They were doing this mechanically through some wheels and wiring with the Enigma machine. Now, you want to use, so this is basically a transposition. A letter goes into another letter, right? And a permutation will be more in line with, let's say we have a certain message that we write in a box, and I'm going to read the message in the other direction. All of this kind of cryptographic systems were known for a very long time. For example, this one was used by Caesar's army in ancient Rome. It's kind of a fascinating thing. So simple cryptography is very efficient. If you don't know how to read it, it looks completely garbled. They basically had just a rod of a certain diameter. They took a piece of paper and wrapped it around the rod. They wrote the message on the rod, and they unwrapped the paper. And that's essentially, you write the message in this way, and you read it in this way. Now, of course, if you know that the rod has been used, it's trivial to read it. It's just, I mean, you don't even care about the diameter of the rod. To some extent, the diameter of the rod is the key. But it's very easy to break it if you know how it was built, because you just try rods of various diameters until the message is in the clear. So I want you to understand that none of the stages are particularly efficient at cryptography. The strength of the cryptographic system comes from the fact that many such stages are interleaved, okay? So that the garbling becomes essentially a nightmare for anybody who tries to break the cryptographic system. So this, for example, this kind of transposition, how would you attack this? So this is easy to attack. You just try messages until they get decrypted. How would you attack this? Now, this has a lot more combinations, so you can't attack it easily by just enumerating all possibilities, right, to create such a mapping. Well, it turns out that statistical attacks work like a charm on this. So what's a statistical attack? Well, you know that the language has a particular distribution of letters. When you have English, right, if you go and do analysis, you're going to see some letters with much, much higher frequencies than other letters. Now, if the message is garbled only on this way, all you have to do is compute, and it's enough to have 100 words or so. What you do is you just go and compute the frequencies of the letters in the 100-word letter, let's say. And you're going to notice which are the frequent ones, and then with very high probability, those are going to be really the frequent ones in the language. So for example, A is very, very frequent. If I see lots of T's, I know that T is in fact A, right? And you just start from one letter, and you break more and more and more and more. And even by hand, within a couple of days, you can actually break a cryptographic system, right? I actually have an interesting story about this. So I was about 11, 12, and I found some encrypted letters from one of my, how do you call them? One of my relatives to some kind of a girlfriend, right? And I was fascinated as a kid by, oh my God, full of signs. Those were signs. It's not even a letter goes into another letter. They were signs. And I simply looked at it for a couple of days, and I said, hey, this starts to look like some kind of words. There was a major problem in the cryptographic method employed there. All the white spaces were maintained. If the white spaces are maintained, you can break it by just guessing the one-letter words. Now, you see, the method was good enough to keep the letters secret for 20 years until I bumped into them, okay? So it was effective, right? But even as a kid, by instinct, you can start to get some idea of what things are. And since it was a simple substitution, this is called a substitution cipher. If it was a simple substitution cipher, once you find the letter, you can just build from there, okay? Just having some knowledge of what the language is. So ineffective, but these two things together, especially when controlled by a key to decide, if, for example, if you have two alternatives of this, and you always apply this, and the key controls which of the two alternatives at every stage you actually apply, you're going to get a much, much stronger cryptographic system. Now, of course, if you apply a few rounds, it's not as strong. But the moment you reach something like 16 to 32 rounds, it becomes extremely strong. So almost all modern symmetric cryptographic systems, more or less inheriting from the Enigma story, right, have these rounds in them. Right? You do something at the beginning, then you're going to do uniform rounds and something to close it up. Some of them don't need the beginning, some of them don't need the end. And the key controls what exactly do you do at every round. So this is this, for example, right? So you have an initial permutation, and then the key is going to control what happens in these stages. So this white space is how the text transforms as you move through. Now, of course, we are using binary computers, so we're going to represent everything in binary. There's no need to actually, so a good cryptographic system wouldn't even care about replacing the white spaces because in the end, it should maintain none of the statistical properties of the original text. So this is going to be a basic requirement for a symmetric cryptographic system, right? So even if you have certain parts that are very, very frequent, for example, the white space is very frequent, right? That frequency should disappear completely. Now, there is a chance to do that because we change our mind how we garble even. So what's going to happen is once you're not going to encode independent words, right? Another principle is you want to chain the encryption. So once you encrypted the word, essentially the state of the entire encryption machine is passed from one encryption block to another encryption block. So you're going to use this as a starting point, XOR it with a new message, and move on, right? This is called chaining. Chaining will make the encryption even stronger. I mean, not much stronger. I'm sorry. If you take, for example, just small pieces of text, just 8 bytes, it doesn't matter how strong your encryption is, how much you garble. If you maintain boundaries of 8 bytes, then you still maintain the frequencies in the original text, right? So for example, Enigma was really, really a big nuisance to break into, because every time you press the key, the wheels were turning. So because the wheel was turning, it was continuously shifting how it actually does this kind of a permutation, right? And the past words that you typed on the Enigma machine influence how the rest of the words are actually encrypted. Now, it's worth pointing out something crucial about Enigma, because you have to understand that everything you do when you use an encryption system, it doesn't matter how good it is, everything you do could weaken the system significantly, okay? So even at the expense of not covering enough, let me tell you the story which you might not know about how Enigma actually was broken. Anybody has an idea of how they managed to actually break the Enigma code?
The later, for example, A was never A in the encrypted text.
Well, I mean, that's one minor vulnerability. So they notice certain patterns, right? That A cannot stay A, so that eliminates some of the things. But it turns out that a big breakthrough in breaking Enigma was related to how Enigma was used, not necessarily an actual defect in the encryption method, okay? So in particular, what they were doing is this, and it makes sense at the operational level, but it produces a vulnerability. So the keys for Enigma were 3-letter keys, okay, so 3 letters, okay, 3 letters of the alphabet. And basically, the Germans were doing the following thing. They had a day key and a message key. Now, the day key you can afford to distribute by some sort of a slow way. So what they did is they published a book. They literally told the guy responsible for the book that you basically get court-martialed if you ever lose this book, okay? So they were distributing in a very secret way with lots of armed people the day keys in a book. So that's fine. Allies never got their hands on a day key. I mean, literally, if they had something like this on a submarine, the commander of the submarine was responsible for the day key logbook, and he was supposed to destroy it. The message key was invented on the spot, okay? So what they were doing is, first, at the beginning of every message, they took the day key and encrypted the random message key, and then encrypting the rest of the message with the message key. Now, they had a pretty good, I mean, first of all, picking the message key can be exploited depending on who transmits it, because people never really pick random stuff, okay? So people are weird, and they have idiosyncrasies in how they pick them, but that's too much dependent on the specific person that transmitted it, and you don't know because they were using wireless communication at the time, okay? You don't necessarily know. They knew some of these things, but not in a big way. The big mistake, though, was the fact that they didn't put, to make sure that the other side can read reliably the message, they took the message key and put it twice in the message. Then encrypted this and switched to the key. So they replicated twice. So they took the free key and free key, the day key, put it twice in the message. In this way, when you decrypt on the other side, you compare the two and you know if you have a reliable message or not, and then you continue doing things. This thing alone probably lost the war for the Germans, okay? Now, it's weird, but these kind of things can actually be exploited, and you know about Bletchley Park and Alan Turing and what they are doing. Right? Well, okay, maybe it's my duty to mention that, in fact, a lot of the glory for breaking the Enigma should not, I don't even remember the name, should not really go to the English. A Polish mathematician discovered this idiosyncrasy early on in the war and find out mathematically how to exploit it. The trouble is, it still involved a large amount of computation, right? They couldn't even do it by hand, so what they've done is they built the first large-scale electromechanical computer in order to try all kinds of versions to do all kinds of things. And in the end, what they did is they studied the cyclic nature of the Enigma. And by just looking at what happens when this key actually got repeated, they noticed mathematical, so it's all about group properties, right? It's all group in the algebraic sense. By the kind of cycles that were forming in the first part, they cataloged the keys, and they were able within 24 hours to find the day key, which means they could decrypt all the messages during the day. And it's all because of this. Later, the Germans figured out that this is a vulnerability in the system, removed it, but by then they became more sophisticated, and they already determined all the cyclic properties of this and so on, and they figured out how to break it without the vulnerability. So the point I'm trying to make here, which I think is more important even than the details, is pay attention to the specifics of how a security protocol is supposed to be. It's not, people don't insist on it because they just feel like it. Almost any mishap can actually be exploited, right? How you pick this key, which is equivalent to how do you pick that public-private key? We're going to come back to that, right? How do you do the random number generator? You have already good software out there. Just have to Google and find the ones that are the the cryptography community kind of vouches for, okay? So it's just a matter of doing the right Googling in the end. You can find truly open source MIT license or BSD license, whatever, to do this, okay? Now, the details don't matter so much. The important thing is these kind of transformations are applied. What comes at the end, it's completely garbled. It's actually so garbled, I mentioned this before, that it looks truly, truly random. So if you want to figure out if you have encrypted portions on a hard drive. You're looking for something that has overly uniform distribution properties at the level of bits. Right? Only cryptographic systems can produce something so uniform in the end. Okay? All right, so multiple rounds, and you push from one round to another. I'm not going to talk about that in too much detail. The important thing is the way the cryptographic system is designed, usually, so and you have two constraints, and I want you to understand this. Multiple constraints, but two important ones. One of them is you want to make sure that you're garbling things really, really well. But another one is you want to make sure that you can have efficient implementations of this. So the particular transformations you pick and the particular functions you pick to apply the stages have to be implementable on modern hardware, because otherwise nobody is going to use cryptographic systems if they are too slow. Okay? So there's always this struggle. If it's too slow, people don't use it. Right? So imagine, for example, that I can guarantee you that your house is going to be very secure as long as you take half an hour to put 15 locks on it. You're going to do that once or twice and then say, whatever, maybe it's not worth it. I mean, the same thing with the cryptography, right? So and this is, by the way, the reason why a lot of websites were not using HTTPS, because it was more computationally intensive on the server. Because of that, it said, hey, too big of a nuisance, whatever. We use HTTPS maybe for authentication or for credit card transactions, but the rest of it goes on HTTP. By the way, I've heard of really, really good news that the new version of the HTTP protocol will be encrypted with no ifs and buts and has to go through certificates and things like this. And you don't even have the choice to transmit it non-encrypted. They are seriously considering this in the new standard. Right. Right, so in DES, for example, the scheme, it doesn't matter. DES is very old. It's 1960s. And it's now easy to break. You can easily break it on your laptop within a few seconds. Okay? At the time, it was strong enough. It was used by the Army for a while. Okay? I don't want to go into the details. Right? RSA is much more interesting. Now, I don't have slides for AES-256. There are some fascinating animations on the web. Again, I don't want you to remember details. I just want you to see it once. It's like opening the hood of the car and seeing once kind of what's in there. Right? I mean, it would be nice if the engine would be transparent. And it is transparent for implementations of AES-256 in JavaScript, in which they show you how all the shuffling and all the stuff actually works. Okay? AES-256, I mean, even skipping all the history and all the other things, AES-256 is considered to be one of the, is the best algorithm that we know of. Can be implemented very fast, both in hardware and in software. We already have hardware implementations, and it really garbles things up in a massive way. Okay? Nobody has any idea how to weaken it even by a little bit. I mean, it's known how to weaken it by a factor of 4 or 5 or something like that. But they managed to mount some mild attacks, statistical attacks on it when it has 6 stages. But the deployed one has 32 stages, I think, right? Or at least 16. So, okay, good. So let's talk about the public key. Now, it's not clear at all that these public keys even exist, because they depend on something that looks almost miraculous, right? Namely, it's possible to do this encryption and decryption with 2 keys. One can be used for encryption, but even you yourself, if you encrypt it with that, you cannot decrypt. But if you somehow have something, you can actually decrypt it. So, not clear at all how this would actually work, and this is discrete, right, so the hardest part of mathematics, arguably, right, is number theory. Okay? Number theory deals with integers, right, operations on integers. You would think, hey, I learned integers in kindergarten. Definitely my daughter knows integers, right? But it turns out that they have extremely nasty properties to capture mathematically and to prove things on, especially when prime numbers are involved. So a lot of these cryptographic systems with public key depend on certain operations that become very hard unless you know something magic. Okay? So in particular, the RSA, and it's worth talking about RSA. The RSA, basically, at heart, it's this. Now, the actual mathematical operations and how the magic works, it's on the slides and it's hard to remember. But the heart of RSA is the fact that you can do magic with prime numbers. So here here is how RSA roughly works, at least how the keys look like. Okay? So the private, you always start with the private key, and the public key is going to be some sort of a transformation over the private key, usually. But of course, it has to be a hard to reverse operation. If it's easy to reverse, then from the public key, you can derive the private key, and you're done. For example, in AS256, there's no way to derive a public key out of that, right? So the private key, let me see if I have it on the slide. Right, I have it on the slide. The private key is going to consist in two prime numbers, P and Q, large primes. I mean, has at the core 2 primes, okay? The private key. The public key, we have it in here. The public key is going to be essentially this N. No, I'm sorry. E is going to be enough to have it. Let me see what I have on the slide. Right, so the idea is from this P and Q, you are going to derive the public key that it's going to, I'm just going to say, it's going to be related to something like the product of P and Q. Okay, I'm not going to go into all the details. The thing is, if you have the product of 2 prime numbers, finding the primes that form the product turns out to be a very hard operation. Okay? Now, this is called factorization. Right, prime factorization. Right? So the problem when the primes are small is relatively easy. I mean, there is this fundamental theory of arithmetic that says any number can be expressed as a product of primes, possibly with powers, right? That's great. But the trouble is, these prime numbers become rarer and rarer as you go higher up and higher up. And a brute force attack, it's actually really devastating. So imagine that these primes have 100 digits, right? To find, I mean, you don't need to find a prime number, which, in fact, you need to form the private public key pair. You need to find the prime numbers, and when multiply, give me these numbers. So you could try all kinds of numbers. You want to make sure that, actually, it doesn't even matter if you check primality or not. Because you know for sure that what you get your hands on, it's a product of 2 primes. You can just try numbers and push them through. If you find any 2 numbers and multiply give you the number, you know that it's guaranteed to be primes. Because if you don't, if this P and Q are not primes, the system is much, much, much weaker because there are many other keys that could open the message. So it's crucial that these guys are both large and prime to strengthen the cryptography of the system. Okay? So finding such large numbers so that when you divide, you don't get any reminder, it's very, very, very tedious. And this is what the strength of this particular public key is based on. Now, we have other public key systems. So if you want to read the details, go on a website and read the details to see exactly how the math works and all of that stuff, right? But the key idea is you need to factorize numbers to go from the public key to the private key. Now, there are even fancier things based on elliptic curves. And this has to do with the fact that certain mathematical problems are very hard to reverse in integers, right? It's discrete logarithms. You know what the logarithm is, right? So you say 2 to what power it's equal to 152, right? So the question mark is really the log base 2 of 152 if you have real numbers. So by the way, the real numbers behave much, much, much nicer than integers. Real numbers are easy. This is why calculus is an extremely well understood part of mathematics. And this is why number theory is really nasty and not understood at all. Because you see, this is very nice. But now imagine that I don't give you 152 here. I give you 3 modulo some kind of a prime, right? Then none of this stuff works to reverse and to find the logarithm. So this is called the discrete logarithm problem. Just one second. Discrete logarithm problem. And it's tremendously computationally hard. I mean, we believe it to be at least NP hard. Yes?
If people previously have some tables, and these tables store all of the prime numbers, and will this algorithm still be efficient?
Good. So clearly, one way to attack it is to tabulate all the primes, right? So by the way, there is a lot of interest to do this. So imagine you're a big government organization, right? Great. And you have lots of money, big budget. You can throw at this, I don't know, at least a couple of $1 billion. You're going to build a big data center, maybe in Utah somewhere, right? Yes, that's a feasible way. The trouble is, these numbers are really large. I mean, they are 100 digits. Even enumerating all the numbers up to that level, it's tremendously hard. Okay? Now, you can be sure that they tried all kinds of things, but it's still considered to be a very hard problem. Okay? So that's what I'm saying is, when you're going to really large numbers, right, it becomes extremely nasty. I mean, a 100-digit number, to enumerate all the numbers up to that level, it might easily bump into the edge of universe. I mean, you have to be careful, right? Normal algorithms don't climb there. So all of these things are predicated on the fact that there is an asymmetry in the computation that goes on, right? Namely, that you can apply the cryptographic system reasonably fast, even though it will take you forever to find the key, right? This is really the idea behind even NP completeness. Well, if P is not equal to NP, and the NP completeness implies exponential algorithm, right? So what's NP? You remember from the class? It's efficient to test, but inefficient to find, essentially. That's the idea, not that it's exponential. It's efficient to test. So it's the same thing here. By the way, factorizing numbers is not known to be NP complete. Actually, I think it's known not to be NP complete. So the story is murkier because there is this in-between polynomial and whatever NP complete is, it looks to be some other stuff that it's hard, that's not necessarily NP complete, right? We believe factorization is hard. Now, somebody cooks up a factorization algorithm tomorrow, we all have to switch to something else. Yes?
I mean, smaller key sizes we can break kind of easy, like smaller key sizes that were probably assumed to be safe when RSA was invented. Like 768-bit, I know is not recommended to use that or anything below it.
Right, but you still, right. So what happens is,
You have to have really big primes.
really big primes, and I need to mention something about that in a second. So the strength of the cryptographic system goes down as the time goes down because of our increase in computational power. Okay? Now, of course, it turns out that our computational power kind of goes up somewhat exponentially, or at least it used to be. Right? So this is why you have to be concerned. So when RSA was proposed, it took a big amount of effort to break even 128-bit keys, I think. That was the first challenge, I think 127 or 128, right? And 700, in the 700s it was considered to be safe. Now the US Army said, hey, safe is relative. The military standard, even initially with RSA, was 2048, right? So that was many ages of universe outside. But all of it can come down to nothing if somebody figures out an efficient algorithm to do this. And it's not clear at all that such efficient algorithms don't exist. But there is another problem here, and I want you to understand what this problem is all about, because that, in fact, incurs a certain penalty when you're cooking up these keys. So we are trying, for example, in JavaScript to use this public-private key cryptography, and the problem we have is we need to generate such keys. Well, it turns out that it can take up to 15 seconds to generate one such key. Okay? So let me explain you why. You see, the key is you need large primes. You don't have large primes, your system is worth nothing, essentially. Okay? Because you need large primes, the question is, how do you find large primes? Now, notice that not only large primes, I want them to be random, because if they're not random, and you know that I'm picking only out of a million large primes, I'm doomed, because you just tried a million large primes. Okay? So to some extent, this is a chicken and egg problem. So there is, again, it almost looks like to find good keys, I need to find prime numbers, but if I have a good way to find prime numbers, then I could break the system. But it turns out that there is an asymmetry based on randomized algorithms that will allow you to, in fact, find reliably large primes reasonably efficiently. Okay? So this is something called primality testing. Right? If I give you a large number, so this is the way it could go. You pick a random 100-digit number. Of course, you have no idea. First of all, if it's even, you toss it. Okay? You never pick even ones. Okay? It's odd. You have no idea if it's a prime or not. So I need some kind of a machinery that reasonably efficiently will say, yes, it's prime, or no, it's not prime. What's that machinery? I can't possibly factorize it, because if I factorize it, I know it's not a prime, right? if I manage to factorize it, but we just argued that factorization is hard. I'm going to pick keys that are so large that even factorizing the subparts is going to be hard, right? You pick 2048 for the kind of the military use. 1024 is how big each of the parts has to be. That also is way outside the realm of what you can actually factorize. So you can't possibly factorize to figure out if this is a prime or not a prime. Actually, you don't. I mean, what you want is to make sure that, in fact, with very high probability, it's a prime. If it happens not to be prime, you have a little bit of a weakness. But, right? Good. So to do that, you use one of these magical randomized algorithms. You bumped into one of them, the push sum. It's the kind of thing that just works. It requires a complicated proof why it works, but it doesn't look like anything that would in fact work. Okay? So there is this randomized algorithm to do primality testing. It's almost pointless to even try to understand it because it comes with very complicated theory associated with it to say why it actually does what it does. Okay? So this is again one of those situations in which you never ever want to implement it yourself because a little bit of a weakness in how you do the primality testing, randomized primality testing, could let numbers that are not prime and in fact they have small factors in, and then this is breakable, right? All that stuff. Or not having a good secure random number generator to actually enumerate things that are candidates that can, right? So when, and you always should, when you need to use cryptography, public key cryptography, my advice to you is find widely available, reasonably well supported implementations of these algorithms and just use them. Now that's basically what we do. I mean, we just Googled for JavaScript public key cryptography. 5 results come. You look at them, you look how well supported they are, what license they have, and so on, say, good, this is the one I'm going to use. Done. Okay? Don't ever implement these things. Unless you're paid a lot of money and you're part of a team that implements it. But right now, I mean, especially AS256 is implemented in hardware, so nobody should, in fact, implement it. Okay? So that's the story about the public key crypto systems, the RSA. I'm not going to go into the details about the elliptic curve. It's kind of details that you can learn and then you remember for a day or two and then they go away because they are complicated. But they're all based on something that's hard to solve unless you have the key. Again, the key here is to know the P and Q separately, not the product. Okay? Knowing the mathematical details for RSA don't help at all, really, in deploying it. Okay? Just remember, finding a key is computationally intensive. Encrypting something with it, it's about 3 orders of magnitude slower than AES-256. So you should use these protocols only to do some sort of authentication. And I want to talk about what could you do to, especially the role of public key cryptography in authentication. It's now used all over the place because of the SSL, right? The SSL certificates. Okay. You know what? Let's discuss a little bit this, because there is a very complicated protocol which does not use public key cryptography, and to some extent it becomes obsolete because of this. Which I need to talk about because it's called Needham-Schroeder. I need to talk about this because inevitably you're asked about, hey, do you know the Needham-Schroeder algorithm for authentication? But let's see how public key cryptography could actually be used for authentication. Let me see if I have a slide on this. Yeah. Well, not really, so let's cook up a story. So the idea with the public key, public-private key, to authenticate is reasonably simple, okay? Well, so there is something that you have to be aware of all the time. Namely, you must know something about the person you're going to communicate with. And that something turns out to be tricky in itself. So you somehow need to escalate some kind of knowledge, trust knowledge, or something like that in order to make any of these algorithms work. And it's going to be clear what's going on when I talk about how things work on the web with the SSL certificates. Okay. So basically, this is the idea. I'm just a normal user, right? I'm going to generate locally a public-private key pair. So we have this notation. So I'm A, right, which happens to be correct. Okay, KA, so I'm going to generate the KA plus and the KA minus. This is the secret, this is the public one. And the idea is the following. I keep this secret, and I might even encrypt it symmetrically with something, so I need a password to unlock it. but I want to make this wildly public. I mean, one way, for example, if I want to implement something like secure email, would be to publish this on my website. Okay. So I can publish my public key on the website and say, if you want to send me emails, you have to use this public key to talk to me. How would you use it? Okay. Well, so we have a little bit of a problem. It's not clear that what key is published on my website is in fact my key. And a way to attack it would be to somehow go and put another key on the website. But let's assume that I'm the only one that controls the website. I publish it. And then it's literally in the open. Or think about something like a phone book. I generate my key, and I make it available, and we put it in a phone book. Okay? Now, if you want to talk to me, and you want to make sure I'm the only one who can see the secret message, what you're going to do is generate a communication pair. This is going to be a secret pair, A and B, your B. Right? By the way, usually A stands for Alice, B for Bob, and these are the characters for all the cryptographic papers. Okay? All the papers. So if you read anything with Alice and Bob, that means it comes from the cryptographic community. Immediately you can start to trust it, just if it has Alice and Bob in it. It's a good rule of thumb. Okay? Literally all the papers have Alice, Bob. Okay? Good. So you pick up a random key, which is complicated. And this key, it's symmetric, and you're going to use a symmetric algorithm to encrypt the message. So you're going to use this key plus, let's say, AES-256 to encrypt the message. Now, of course, that's great. The message is encrypted, but how am I going to read it? Because I don't actually know the key A and B. So what you're going to do then is encrypt with this key, with my public key, you're going to encrypt the key AB. Not the message, just the key. And you attach it to this symmetric key applied to the message itself. So you glue these things together. We can talk later more about how you can do this so you cannot detach the head and the body and make sure other things are there. But for now, you're not. The only worry is I'm the only one who can read the message, right? So you generate a key, you encrypt it with my public key, and you attach it to the message, and the message is encrypted with that key. Now, the assumption is if you don't have this key, there is no way to attack and find the message. There's just no way. It's AES-256. And also, the assumption is if you don't have the private key that corresponds to the public key, there is no way to attack this message. Now, the nice thing in this scheme is this can be truly public information. And you cannot derive the private from the public. This is why I can publish it like a phone, like in a phone book. Okay? Now, when the message gets to me, there is no way I can unpack the encrypted part unless I figure out what the key is. To figure out the key, I have to apply the transformation to the header. So I need to do a KA minus applied to KA plus applied to KAB. Essentially, this rule will cancel out. And then I get this key, and then I can apply the symmetric cryptography to decrypt this, right? This is really at the basis, at least in a very crude way, of what goes on in secure email implementation, okay? Now, there are a number of problems here. One of them is, how do you really know that this is my key? Because you see, you want to tell me something that's secret. That's great. But if I trick you and I put somebody else's private key in here, I mean somebody else's public key, and you encrypt using that public key, of course that person can read it, right? So now it's crucial to make sure that nobody else can in fact pretend that they are me and put their own key in there, okay? So that's one of the problems. No, that's one of the problems. The other problem is there is nothing in here that tells me who sent the message. And it might be important to add elements to such protocols to ensure the fact that I know the message comes from B. So I have here K, A, and B, but how do I know it's B and not somebody else? Right? So interesting questions here are, if two parties want to communicate, is it possible to escalate this with an even more interesting protocol in which I know you are, who you pretend you are. You know I am who I pretend I am. And we also do secure communication for the channel. Okay? And these ideas lead to something called digital signatures. Now, digital signatures is not cryptography. It's to some extent the opposite of cryptography. So the idea in a digital signature is, if I sign a document, anybody can check my signature on the document, but nobody can forge my signature on the document. Right? We are going to discuss that on Thursday to see how that works. But it turns out that all of these goodies come out of public key cryptography. So all of it can actually be done, okay? Just using the same strength of the public-private key cryptography, okay? So just to give you an idea, the way I can digitally sign is by encrypting with the private key, and then anybody can decrypt with the public key because there is some symmetry in there. You can decrypt with the public key and check that it's correct, but you cannot cook up what I put in there without the private key, okay? We're going to come back to details later. Okay, so notice the performance part. You still use symmetric algorithms. This is why you always see them in pairs, right? You're going to see the use of public key cryptography, RSA or elliptic curve, together with AES-256. There is no, you can't replace something like AES-256 because you're not going to be efficient. This encryption process is thousands of times slower than this encryption process. That's the idea. Because essentially encrypting this means doing operations with very large powers of numbers. You're going to literally take powers of those 100-digit numbers. I mean, that's not something that can be done particularly efficiently, right, to encrypt a message. Okay, good. Now, let's look a little bit at the question for 4 minutes, at the question of how can I make sure that I know whose key is there? Because here is the counterpart on the web. I want to establish a secure communication with, let's say, Amazon. Okay, that's great, because I want to buy things. I want to make sure nobody can eavesdrop. In order to do so, I am going to run something equivalent to this protocol in which, in the first stage, we are establishing a communication key, and then we use it for whatever number of minutes for the session. Okay, this is called the session key, right? So in order to do that, I have to grab the public key of Amazon and apply it to something I invent and send it and establish the protocol. Now, how Amazon makes sure I am who I am, that's a different story, and usually no public-private key algorithm is used for that, something else like a password or whatnot, okay? But how do I know this is Amazon's key? Because one way to make sure you get people's credit card information is to pretend you're Amazon. People go on a website that looks very much like the Amazon website. Immediately they get to type credit card numbers. How would you know that is the real thing or not the real thing? And then, oops, I got your numbers. By the way, interesting precedent in Romania. Not with websites, with ATMs. When you go to an ATM, how do you know it belongs to the bank, by the way? So the story goes like this. In Romania, a bunch of really bored guys designed from scratch a complete ATM machine with software on it that looked very credible and placed it at various locations in Bucharest. Within a few days, they harvested lots of ATM numbers with the pins. All you have to do is you put it in and pick, sorry, error or some detail or some other detail. Or your pin is incorrect, but you already got their pin, okay? It's the same thing here. So in order to solve this problem, you need somehow to do some sort of trust management. Somebody has to verify that this indeed it belongs to Amazon. Or imagine that I pick a public-private key pair, right? I need to publish somehow my public key. And it has to be something that cannot be forced. Somebody has to vouch for me, that they know me, and I certify the fact that this is this person, and then you put it in a place and that's controlled, nobody can change. This is where this kind of companies like VeriSign come into play. So VeriSign, essentially what it does is, for the right amount of money, they will, when you generate a public key, they will attach a so-called certificate to it to say, we verify that these guys are who they say they are, right? Now, the verification is like a digital signature. Then the only thing I need in order to make sure that your key belongs to you is to verify using, in fact, the public key of VeriSign. So I just need to know the public key. You need to know the public key of somebody. By just knowing the public key of VeriSign, which it's extremely stable and it's guarded with the life of the people that deal with it, right? You verify with the public key of VeriSign by verifying the signature on the certificate these guys have. So these guys are not going to publish only their key. They're going to publish the key together with the certificate signed by VeriSign that the key is genuine. Okay? So when you buy an SSL key, what you're buying is the privilege to use this mechanism for other people to make sure you are who you are. So when you look in the web browser, if you have a HTTPS, it's going to show you the log. But not only show you the log, it's going to show you in green, red, or other colors. And if you click on it, it will tell you what it verified and what it didn't verify. right? And it turns out that these keys, VeriSign wants these keys to be bound to domains as well. So you can register a key per domain. So we bought such a domain, for example, for my company, right? And you cannot move it on another domain because then the browsers are going to say, you know what, this is a very wonderful key, but it doesn't match the domain. Oops, right? So you need this kind of a trust authority. I'm going to come back to this later. Otherwise, again, it's aliens in the skin of humans. How do you know you are who you are? I mean, somebody has to certify it. And VeriSign might even ask for physical proof, by the way, IDs and stuff like that. Right? It's a whole hullabaloo with how you get one of those keys. More of this on Tuesday, no quiz, because I want to have more material to quiz you off, because I'm going to have only 2 more quizzes, right? One on the security and one on whatever we cover until the end of the class. Okay, thank you. And read more about this.